We present RSLAM, a computational imaging system for arcminute accurate eye tracking using video of the human retina. In this work, we introduce AOSLO-based eye tracking to the computer vision community, improving upon prior methods developed in the field of biomedical optics. For context, most conventional eye tracking systems are only accurate to 30 arcminutes of visual angle or more, making them ill-suited to resolve eye movements like microsaccades and fixational drift. Unlike these systems, the Adaptive Optics Scanning Laser Ophthalmoscope, or AOSLO, directly captures video of the retina at the cellular scale, allowing eye tracking at arcminute precision. The AOSLO zooms into around 1 square degree of visual angle, scanning the retina with a laser in a top-down fashion, which results in rolling shutter artifacts that manifest as warped cone cells in each frame. The upside of this rolling shutter is it enables motion tracking well beyond the frame rate of 30 Hz, but the retina's motion and appearance are entangled in a single data stream. Our framework, RSLAM, models and inverts the AOSLO's video capture process to jointly estimate the motion and appearance of the retina. Mathematically, if we let M and R be variables for the motion and retina map respectively, then we can define an operator f that represents the forward model, where f of m, r is the video generated when retina map r undergoes motion m. RSLAM's objective is to reconstruct the input video v as closely as possible. The algorithm proceeds in 2 stages, using dense feature tracking to get an initial estimate for the motion trace, then refining this estimate with gradient-based optimization. Optimizing our objective using random initializations for the map and motion fails to converge, so we initialize both to values that are close to the true solution before running gradient descent. This is done by tracking patch features across the entire video using normalized cross-correlation, then aggregating these features row-wise and removing outliers using ransack. Next, for each tracked feature, we set up a tracking objective that aims to fit a motion trace from the feature's displacement over time. Geometrically, feature displacements in frame space are equal and opposite to the eye's displacement in world space. To make all the features as motion traces consistent with one another, we impose a Brownian prior on consecutive features. Combining these losses results in a convex quadratic program that is easily solved with off-the-shelf packages. We refine the initial motion estimate using gradient-based optimization. As before, our objective is to reconstruct the observed video v. Now, define S to be a stabilization function where S of m, v is the map produced by stabilizing and averaging the video frames of v according to motion m. If m star is the true motion trace we're solving for, and r star is the true retina map, then we can approximate r star by stabilizing the video v according to the motion m star, given enough frames. If we use this approximation for r in the objective, then we no longer have to optimize for the retina map. It's implicitly learned by just solving for the motion and using the stabilization function to produce our current map estimate. Because the retina map often contains hundreds of thousands of parameters, solving the original optimization problem fails to converge, whereas the new one does so in an efficient manner. The new objective is optimized as follows. We take the initial motion estimate m and input video v and generate a map estimate using the stabilization function s. Next, we reconstruct the video using the forward model and compute the error by taking the squared differences with respect to the input video. Finally, we perform a gradient step to update the motion estimate, iterating this entire process until convergence. We compare RSLAM to prior work. Shown here are the stabilized videos output by each method, as well as a visualization of the stabilized retina map being accumulated over time. Tracking error shows up as blurry artifacts in the stabilized maps. Note that these maps are generated by stabilizing and averaging all the frames in order to illustrate the quality of the motion traces. In practice, other methods typically drop frames to improve the map quality, but because we wish to track the eye across the entire video, we compare the methods using all the frames. We also evaluate RSLAM's performance on retina map estimation alone, in which frame data can be dropped. In this case, RSLAM still produces higher quality maps than Stevenson and Bedgood et al., avoiding the seams and blurry artifacts that arise from those methods. When evaluating RSLAM before and after the gradient-based optimization step, we find that this step improves the system's ability to resolve individual cone cells and remove residual blur. Quantitatively, RSLAM offers the best results over prior work, both in simulation and with real AOSLO video. To conclude, RSLAM solves for eye motion by inverting the AOSLO video capture process using optimization. Our novel Convex Initialization and gradient-based refinement algorithm outperforms prior work in this area. However, it's important to note that the AOSLO has limitations. It's a tabletop device rather than a head-mounted display, and can only image a narrow field of view unlike other tracking systems. Nevertheless, the AOSLO combined with RSLAM form a computational imaging system offering the most accurate eye tracker in existence, enabling the collection of ground truth eye motion data that can be used as priors in other less precise tracking systems, and more broadly in the field of computer vision.